All right, guys. My name is Brian Cain. I work at Qualcomm on QEMU Hexagon, and I'm here today to talk about QEMU system, Hexagon system emulation. So, first off, where are the Hexagon cores used today? In Snapdragon and Dragon Wing processors, they're used for energy efficient computing for several different functions, including the cellular modem functionality, AI inference with the compute DSPs, computer vision, and more. And for starters, I'm going to talk about the initial use cases for QEMU Hexagon and the machine setups that we're upstreaming now. So with the Hexagon SDK, we ship QEMU Hexagon and Hexagon Sim. Hexagon Sim is a legacy instruction set simulator that is roughly cycle accurate, and it's used during silicon validation and other architecture developments. And it's sort of the basis for some of the use cases that we have for QEMU Hexagon, at least to start with. So you might have an algorithm developer who wants to port some algorithm to the Hexagon architecture, and today they use the Hexagon SDK for that kind of thing. It'll either boot sometimes a simple bare metal operating system or an RTOS developed by Qualcomm that's called QuRT. And another use case beyond algorithm development is regression testing for the operating system itself. So we have two initial configurations we're starting with. One that's sort of a real configuration. It's an automotive SoC DSP used for computation offload. And it uses a real memory map. And then the QEMU Hexagon VIRT machine, which is sort of a hacker space, maybe for somebody who wanted to work on Linux kernel development or something like that. And to recap, if you're not familiar with the Hexagon ISA, it's a 32-bit very long instruction word ISA, and it can have as many as 4 instructions grouped together in a packet that gets dispatched together. There's a code size optimization that the first word can have 2 16-bit sub-instructions. And then there's some sort of complicated rules about which instructions can legally be grouped together with one another, and the assembler works out all of those interesting details. Some little bit more information about the ISA. So the user space instructions are already supported by QEMU upstream. And there was a previous presentation given by Taylor and Nicolo, and I've made a reference to those on the slides here from previous KVM forum. But for folks who haven't seen it, I've put 2 examples of some instruction packets up at the top here. I'll talk about this first one, a swap. So there's 2 register transfers there, and the semantics are such that the registers are read, and then some computation happens, and then generally register values are written. The syntax looks a little bit like C, where you have sort of expressions on the right-hand side of an equal sign and a destination on the left-hand side. And so this first packet here is truly a swap. Register 3 gets its contents ended up in register 2, and register 2's original contents end up in register 3. The packet on the right side is a little bit more complicated. It has all 4 instructions filled. So there's a comparison that gets its result put into a predicate register. There's a predicated jump instruction. There's a predicated load instruction, the second one there, and that one uses the predicate result from the previous instruction word that's shown there. So instead of many of them executing independently, you can actually have some serial dependencies that are indicated. And that's why you see the .new reference there. If the .new were omitted, it would actually use the P0 predicate value from the before this instruction had started. And at the bottom, there is a complex multiply that also has a shift ground saturate associated with it. So that is a legal user space packet up on the right, and that's part of what already exists in QEMU today. What's new that we're working on is upstreaming support for system emulation. So I basically just took, for the example, the same sort of packet and replaced one of the words with a register transfer that includes a system register. I'm not going to go into the details because I forget what system register 1 actually does, but I'm sure it's something really interesting, I'm sure, and it's part of sort of the complication of including global effects sometimes along with sort of the simpler effects of the rest of the packet instructions. Now, the good news is that the really, really interesting system instructions are required to execute on their own, but some of the simpler ones, like the register transfers, are not. What other parts of system emulation are there? Sort of things you might expect: TLB instructions, interrupts, exceptions, instructions that deal with cache. Even though the cache isn't modeled, some of the semantics are sort of dependent on the metadata associated with the cache is modeled just to preserve the general behavior of the instructions. There's some locking instructions that are able to start and stop threads, hardware threads rather, wait for interrupts, and semi-hosting. Generally, a lot of the use cases that we deal with rely on semi-hosting. So I've got a sample machine here, and there's a lot going on, so I'll try and talk about all these pieces. The ones in green are ones that we have modeled, and the ones in red are ones that we haven't modeled, could conceivably, don't have a use case for yet. So we have instruction cores and we have HVX context. The HVX is the vector coprocessor, and the core threads sort of oversubscribe the HVX context. There's generally fewer HVX contexts than there are threads to execute those with, and so those can be bound dynamically at runtime by the operating system. At the interrupt controller, we have a timing source, and then we have a bunch of memories. There is a tightly coupled memory that's used sometimes for instructions, sometimes for general data, sometimes when you operate in the absence of a DDR, a powered DDR system. And then there's the vector tightly coupled memory, which is used for the vector coprocessor and more. The config table is a ROM. It's sort of like feature bits for what's the capabilities of this system, how does it exist in the context of the SoC. There is a UART that, to my knowledge, is never used by production software, but we tend to use a UART when we're doing some sort of experimentation with QEMU. There's the main memory, the DDR, that contains the instructions, but then also generally the data that's operated on. The ARM SMMU is, I mean, of course, it is modeled in QEMU. We're not leveraging it in Hexagon machines. There's no real use case for it yet. And then we have an interrupt relay function here, this IPCC. Generally, in the real context of a device, you would communicate with the Hexagon DSP by loading some content into DDR and then sending an interrupt relay via this IPCC. The transactions are usually called fast RPC transactions at some of the higher level layers, but that's the underlying mechanism. The SMMU providing some mapping to some window into DDR and then sending a relay either to the DSP or from the DSP to an application core or some other core. And then very similar to the compute DSP that I showed before, is a vert system that has slightly fewer pieces and then a couple of extra pieces. So we have a synthetic device tree that's similar to how other architectures create a dynamic device tree blob. We have VertIO devices, and then all the same timer and memories that were there before. Oh, yeah, yeah. So bootstrapping. On the real device, you'll have the DSP held in reset usually until the supervising processor will load some code into memory from disk and then program the vector base and then bring the DSP out of reset. In QEMU, we have roughly similar. We have an ELF loader so that the system can operate independently that takes the kernel argument, takes that start address as the initial PC. Typically, the SMMU in a real system is also programmed by the supervisor to let the DSP have access to its region of code, and we bypass that functionality for simplicity's sake because the guest programs that we're running don't generally interact with the SMMU. So I have a couple of real simple examples here, which are the kind of things you might do with the Hexagon SDK and QEMU Hexagon. So it's a trivial C program that you would build hello world style. And with Hexagon Sim, the arguments that you would forward are slightly different from how they're forwarded with QEMU System Hexagon. But ultimately, you get the same sort of behavior from this standalone OS, this bare metal environment that comes with the Hexagon SDK. Slightly more interesting is the QuRT loadable SDK program. So if you look at all the examples, there's more along this line of things with the Hexagon SDK, and it's unfortunate that there's a little bit more activity going on, that you have sort of an initial bootable OS, run elf.pbn. It loads a second stage, run main on Hexagon Sim, and that second stage is the one that loads the shared object that contains the user's program. And that reflects how those programs get dynamically dispatched onto a real DSP. I mentioned semi-hosting before. The good news is that our semi-hosting implementation in QEMU is relatively non-disruptive. It fits sort of in with the existing semi-hosting support. There's a couple of extensions that have been added for Hexagon, and I don't even know for sure if those are critical, but we implemented them anyways. There are some tests that would exercise them. There is special behavior for the sys open. So we saw on the previous slide that, for example, you might load some shared library. It could have a series of dynamic dependencies that get resolved by the loader. And the way that it was solved in the previous existing design with Hexagon Sim was to hook the open call for the loader to be able to have a search path specified for the dependency libraries like the C library, the C++ library for the target. So that's the sort of special hook that we have for sysopen. And when we get to the point where we are pushing those patches to the list, we'll be looking for feedback about maybe how that could best be done, but we're modeling the existing behavior of the Hexagon Sim. So unfortunately, it might become a little bit of a theme for this talk, but the spec for the semi-hosting is available any day now. I promise we'll have it real soon. Hoping to have it before the talk. Didn't quite make it, but we'll have it real soon. I promise. Some of the system features that have been modeled. So I mentioned to some extent before that there's multiple hardware threads, simultaneous multi-threading. This is, I think, pretty vanilla in terms of QEMU. They're just more vCPUs. There is a dynamic mapping between the threads and the HVX contexts. There has been some discussion on the list about how best to handle that when context switching happens. Where should we store that state? Ideally, we want to be able to leverage TCG, and at the time we started that discussion, there was not a capability to handle the multiple indirection that we would need. So we had sort of hacked it in there with global variables, which was effective, but might not be the right way to do it. So we'll continue to discuss that as well. There's a hardware schedule functionality or a scheduler assistance functionality from the DSP architecture, and it includes an interrupt that gets raised when certain scheduler conditions exist. So there are registers that describe the priority of this particular thread, and whether or not threads are in a waiting condition. Interrupt steering, when that scheduler functionality is on, the interrupts get handled by the lowest priority threads first. There are some locking instructions. So there's a special instruction for things like an OS, big kernel lock, and then there's locking for TLBs as well. The Hexagon VM. So there is a virtual machine interface for Hexagon that's been specified, and that's what was targeted by the Linux kernel port for Hexagon. It has a lot of details so that instead of having an architecture that is, let's say, set in stone, the ISA and to some extent some of the ways that the hardware work might change in some backwards and compatible ways, and has changed in some backwards and compatible ways. So to save the OS kernel from having to worry about that, these details have been abstracted into a virtual machine, and the specification is published, but it is a little bit old, and we expect it to be updated again real soon now. That one I expect to probably take certainly more time than the semi-hosting spec, because it's not in our team's main domain. One thing I'd really like to look into is implementing this VM interface in QEMU, so having QEMU handle the hypercalls, maybe instead of implementing it in software in the VM. So the regression testing that's available in the patch series today, we were asked to add support for this boot serial test. So that is a real minimal sort of create some UART traffic activity. We also have a series of tests that could be bound to check functional that are, some of them are derived from test failures that we encountered while bringing up the real-time operating system, and in different use cases, exercising some of the features that are there. So I mentioned the VM interface. We have an initial implementation of the VM, and it's called mini VM, and it has a series of regression tests for it, and those are pretty good ways to exercise QEMU Hexagon. So those are ones that we've added as check functional as well. We can boot to a shell with the Linux kernel, but that's critically dependent on the progress with the VM, and at least the current state of that mini VM is not quite there yet to be able to get to the shell. And we also have, there's a public project called RCore OS that has a Rust implementation of some Virteo drivers, and so we have a contribution there that we can use to exercise Virteo devices as well. One thing we were asked about in the past was verification, and a typical tool that's used is called RISU, is my understanding, for a lot of other architectures. Because of the way that the instruction packets are designed, the encoding space is really, really big. but the valid encoding space is smaller, and it's sort of, I think, challenging to describe. So the way that the RISU project works is, my understanding is that, opcodes are sort of templates that get filled with randomized values to exercise the behavior, and between QEMU and a reference platform, it's verified at various stages. We have implemented something that's similar conceptually. We take, instead of hardware, we take the reference simulator called Hexagon Sim. We generate lexical instructions for the assembler, and maybe blindly or semi-blindly, according to the resource rules, let the assembler just discard programs that aren't valid programs. And the ones that it accepts are ones that we were able to run under the debugger and compare the state of the registers at various breakpoints between Hexagon Sim and between QEMU. When we first started to run this, we found several bugs in QEMU, of course, but then also in things like the assembler, Hexagon Sim itself. We did find at least one particular bug. This one, I meet it real soon now. Like, it could be any day, I swear to God. Trust me. But I apologize. It is a bit of a theme. So the upstreaming status. One of the bigger changes we were asked to make is some of the global objects that we had used. We had a design that wasn't appropriate for a couple of reasons. At least one of them was the heterogeneous TCG that we could eventually get to. But we've addressed that particular one and revved it earlier this week. We sent a new set of patches. Looking forward to feedback there, but we also left a couple of issues identified with V1 that have to go get addressed. So we'll get those taken care of as well while we work on V3. After those in the queue are the set of patches for semi-hosting and the set of patches for HVX support. Those should be right after that. And we have staged a branch that's public that gets frequently rebased, that has these features sort of ready to go. And probably got a little bit of time here. So against my better judgment, I decided to slide a demo in at the end here. And let's see how that goes. Stand by. Oh my goodness. Can we turn that off? What if we do that? That work? Oh, I have to share that, I bet. Okay, great. Okay. Okay, so it's a little bit naughty, or maybe even really naughty, to show you the Linux kernel and then also tell you, by the way, even though it is booting, we can't give you all the pieces that you need to be able to boot it. Shame on us, for sure. We're working on it and we will get it. I just wanted to share a taste. It does work. Never mind that error. That's not fatal. It's not fatal. It happens every once in a while. It's okay. It's probably a kernel bug and not a QEMU bug. The bad news is the kernel team is the same as the QEMU team. So we're gonna have to figure it out one way or another. But let's see. It should come up real soon now. Drum roll. File system check, maybe. Be patient. Getting there. Rule of demos. It's probably going to blow up, but I swear it worked right before. Okay, so we got to a shell, and from the hosts, we can get a uname output. And of course, we have to confess, this is, yes, a very old kernel fork. Yes, yes. The good news is, so the kernel sources are public, hooray. those are in my tree. You can use those, but it's not very much use to you without the critical VM. So we'll get that real soon now, I promise. What else can I show here? So we have the network interface. And so perf, in my opinion, awesome tool. Linux should be really proud that it has this tool. Maybe those of you working on really popular architectures take it for granted, but it's something kind of new and cool for Hexagon, at least for me. So this is not rocket surgery, like I said, to those who are sort of used to it. Oh, boo. Yeah, you might have to take my word for it that it can work. Well, that's another one that worked earlier. What it would show you is that the most samples were in the critical region. Let me see here. So the source of the program that we're running here is a sort of a fairly simple program that's determining if a large number is prime, and we're spending a lot of CPU cycles here. Perf shows you that as expected, which I probably didn't add enough iterations to the loop, and that's why I didn't find any samples. But that's basically what I wanted to show. So the demo sort of worked out, I guess. Yeah, and I'm ready for any questions that anybody might have. Oh, I should have mentioned that one when it was earlier. Yes, no, it's not a commercial priority. There's no customers who are using it, and Qualcomm, to my knowledge, has no plans to use it. So that is one unfortunate reason why it doesn't get too much love, is that it's not a commercial priority. Go ahead.
Then when you were talking about verification, you mentioned LLDB.
I did. That is true. So, and that is one of the ways that we've done verification in the past. In my opinion, sifting through, gigabyte long traces that contain, let's say, millions of instructions of the bare metal bootloader program are much less interesting than just skipping ahead to the points, the critical points in the dynamically generated, randomly generated packets that are worth comparing. So that's where I think we get a lot of value and are able to find a lot of bugs relatively quickly. Any more questions? So also the other one is in there as well. Yeah. Mm-hmm. In practice, they're awfully similar. Just some small changes, like things like the UART and the device tree. Oh. If you're extraordinarily patient, yeah, but yes, you do need the VM. Yeah. Yeah, it takes quite a while to boot, but yeah, when we were first bringing it up, we did sometimes run some comparisons with Hexagon Stand. All right, thank you for your time.